Gen Chem 1 students, as we talked about in class yesterday, the van der Waals equation, which accounts for non-ideal gases either at very low temperatures or very high pressures or both, where interactions between molecules start to play a considerable effect on their properties. The van der Waals equation helps to account for those deviations from Pivner. This problem wants us to solve for the pressure, which means the first thing I have to do is take the van der Waals equation. Pressure plus some constant A for our gas times the number of moles squared times the volume squared, or divided by the volume squared, multiplied by the volume less the moles times this constant B specific to our gas multiplied together is equal to nRT. We want to re-solve this to get P. The first thing that I'll do here is I'll divide this V minus NB to get it to the other side. I get P plus AN squared over V squared equals nRT over V minus NB. It can look a little confusing since I put those parentheses back on, but this is now just one term, and so to get P alone, I need to subtract AN squared over V squared from both sides. So the equation that I'll be starting with is nRT over V minus NB minus AN squared over V squared. Now I have all of my numbers for N, R, T, V, N, B, and A given to me in the problem, so this is a matter of plugging them in and solving. To draw a little bit of contrast, I'm going to do this one in black. Our pressure is equal to the number of moles, 6.49 moles, and I'm going to be trying to show all of my units here, times R. We may need to be specific about which R we use, and since we see a lot of units of liters and atmospheres, that means the R value we want is 0.8206 liters times atmospheres per mole Kelvin, times the temperature. Our temperature is not already in Kelvin, so I need to add 273 degrees to this, 0.15, which gives me 583.15 Kelvin. You can see I might be running out of space here because I have yet to plug in anything for this A times N squared minus V squared term. This is all over the volume, 6.75 liters, minus the number of moles, 6.49 moles, times this B value. This is specific to the gas, and in this case, its value is 0.0237 liters per mole. Minus, I'm going to put this whole unit in brackets, and now this unit beneath it I'll put in brackets as well. A, which is given to us specific to this gas as 0.0342 liters squared times atmospheres divided by moles squared, times N squared. N squared is 6.49 moles squared, divided by volume squared, and my volume was 6.75 liters squared. Here we get some calculator exercise. Here's what I'm going to do. I'm going to take this piece at the top and this piece at the bottom. I'm going to solve those and then replace them. I'm not going to actually do the division yet. And then I'll do the same thing for these two pieces. So I'm going to end up with the same equation, um, but just fewer pieces in it. First, let's make sure that units all cancel. I have moles multiplied by 1 over moles, and I have Kelvin multiplied by 1 over Kelvin. On the bottom here, I have liters minus moles times liters per mole. So that's moles times 1 over moles cancels. This will give me liters minus liters. The usefulness here is that this subtraction has the same unit, which means that this subtraction will have a unit of liters, and I have liters divided by liters. I'm going to save that for a little bit. I'm going to show that this bottom number has units of liters because I'm going to solve for it, and then I'll cancel liters later. Down here, I have moles squared times 1 over moles squared, and I have liters squared over liters being squared. I'm going to show that in the next step as well. 6.49 times 0.08206 times 583.15 I want to try and save as much rounding as possible for later on. If I'm keeping track of my steps, this is going to be step number 5 of rearranging my equation. Pressure is equal to 310.5678, and the units that I was left with liters times atmospheres. Divided by, first I'll take 6.49 times 0.0237. That gave me this fraction, and I'll do 6.75 minus that answer. Now, if your calculator doesn't allow you to go up and choose that answer, you might have put this in as 6.75 minus, in parentheses, 6.49 times 0.0237. End parentheses, and I get the same number. This again has units of liters. I'm going to try and avoid as much rounding as possible. 6.59, 6187 liters. Again, that's all one piece. Here I get, I'm going to first take 6.49 and square it, and then I'll multiply this by 0.0342. This gives me 1.44. Oh 0507. Now let's come back and talk about the units a little bit more here. I've just squared moles and then multiplied it by 1 over moles squared. So I'm going to cancel the moles squared, but I'm left with liters squared times atmospheres on top. Divided by, on the bottom, I'll take 6.75 and square it. That gives me 45.5625. Because I squared liters, I now have liters squared. On my left-hand term, I've got liters over liters. I've got liters squared over liters squared on my right-hand term, which means I'm only left with one unit, and I'll be doing a subtraction here. Now I'll take these numbers and I'll plug them back in. If your calculator allows you, you don't have to even worry about taking what numbers you might have rounded. You can go up and grab these numbers from where you had them before. This gives me 47.0892 atmospheres minus 0.0316 atmospheres, and when I take that subtraction, I get a final pressure 47.05 atmospheres. Does that seem like an incredibly high number? That's okay. We're at an incredibly high temperature. Temperature and pressure are directly proportional. So at high temperatures, I might expect high pressures. I also don't have a very small number of moles. Remember that at STP, 1 mole takes up 22.4 liters. I have much more than 1 mole. I have much less than 22.4 liters. I have a very high temperature. I should expect a fairly high pressure. Remember that this van der Waals equation is not on the Unit 4 test, and it's also not on the final exam, but it will show up on your Real Chem homework, and so I want you to have something to model as you solve these types of problems. If you're given a problem where you have to solve for volume, it's a little bit more challenging because volume shows up in more than one place. That's why it's much more common that you either solve for pressure, or you solve for moles, or you solve for temperature. Happy studying.